Today we're going to talk about one of the applications of integrals. Besides finding the area, we can find the volume of solids of revolution. Solids of revolution are solids that have a rotational symmetry around one of the axes. It could be the x-axis, it could be the y-axis. So we are going to use integration to find those. Say the function in white, f of x, is the function that we want to rotate. When we rotate it around the x-axis, we are going to get a solid that will have a circular base like that, where the radius of that circular base is going to be given by the height of the function at any value x. Now, say we only want to rotate the part of the function that goes from a to b. In that case, our solid would look something like this. It would have a circular top, a circular bottom, and the walls are going to be marked by the progression of the function from a to b. The approach we're going to take is by dividing the volume that is generated at rotating the function into several disks. Each of these disks are going to be equivalent to the rectangles that we took when we were deducing the formula for the area, or when we were deducing the definite integral. The idea would be that we are going to generate as many disks as possible in order to estimate the volume of the solid that we get with the rotation of the function. And the more cylinders that we take, the more accurate our volume is going to be. So after adding all of the volumes of the small cylinders or the small disks, we are going to take the limit when we have a very, very thin, infinitely thin cylinder, and that should give us the volume of the function as an integral. Then we're going to be able to find the volume of a solid of revolution by calculating the integral from a to b of pi f of x squared dx. F of x squared, remember, is going to be the radius of each of these cylinders, and because we're taking the limit, our sum of all the individual values of these cylinders become a continuous sum. Now we're going to move on to a few examples to see this formula in action. In our first example, we're given the function f of x equals x squared. The first question that they want us to do is find the integral from 1 to 2 of f of x squared dx. So we can do that in this space. Integral from 1 to 2 of x squared with respect to x would be the same as the integral from 1 to 2 of x power 4 with respect to x. And using the power rule, that is x power 5 over 5 evaluated between 1 and 2, that is 2 power 5 over 5 minus 1 power 5 over 5. That is equal to 31 over 5. Now for the second part, they ask, the following diagram shows part of the graph of f. This is part of the graph of x squared. The shaded region R is enclosed by the graph of x squared, the x-axis, and the lines x equals 1 and x equals 2. Find the volume of the solid formed when R is revolved 360 degrees about the x-axis. So we are rotating this in this direction. That means that the volume of revolution is going to be pi integral from 1 to 2 of the function squared with respect to x. So we already calculated this integral in part A. So the volume is going to be pi times 31 over 5. So the volume of our solid R is going to be 31 pi over 5. Another possibility would be to rotate the function around the y-axis, and in the next example we have test that. We are given the function x squared minus 9 for x bigger than or equal to 0, and this is the graph of that function. The region R that we are building is between the y-axis and the function, and it's bound by the lines y equals 1 and y equals 2. And now this region is going to be rotated around the y-axis, not around the x-axis. So the integral that we want to use for this exercise would be, say the volume is pi integral from 1 to 2 of f of y squared dy. Now, because the rotation is around the y-axis, my function has to be of x in terms of y. And the function that we are given is y equals x squared minus 9, can be changed keeping x as the leading variable like this. So x would be, and then we're going to take, because these are the positive x values, right? We are going to take the positive square root of that expression. So positive square root of y plus 9. Now this is the function that we have. This is f of y, is root of y plus 9. So when we want to find the volume, what we have to do is substitute in our integral. So that is pi integral from 1 to 2 of y plus 9 in a square root squared dy. The volume is going to be pi integral from 1 to 2, and then these two functions are inverse of each other, so they cancel, and we can just get y plus 9 dy, and that is pi y squared divided by 2 plus 9y evaluated between 1 and 2, and that is pi 2 squared divided by 2 plus 9 times 2 minus 1 squared divided by 2 minus 9 times 1, and this is equal to 21 pi divided by 2. That's the volume of the solid rotated around the y-axis. One thing we can do is create solids of revolution that are hollow by rotating the area bound by two different graphs. And the solid that we're going to form by rotating this around the x-axis, for example, is going to be hollow because this area is not going to be counted. So how do we find the volume of that solid? Keeping in mind that this volume will refer only to the volume of the wall, then the volume of the solid is going to be found by considering the volume of the outer function. In this case, that function is f of x, and taking away the volume of the lower function. In this case, it's g of x. So we're going to calculate those two volumes and we're going to subtract them. In the integral, this looks like the volume is pi integral from a to b of, first we calculate the volume of the function f of x, so f of x squared, minus, we take away the volume of the function g of x squared, and this is the new volume. Let's calculate the volume of the solid obtained by rotating the region bounded by the parabola x squared and the square root function y equals x around the x-axis. So graphically, the region that we want to rotate is bound by the two intersections of the two functions that were given. So the function x squared is like this, and the function root of x is like this. So the area that we are rotating is enclosed between those two intersections. This is the area R. So the first thing that we have to do is figure out what are these values. So it's easy to see that a is going to be 0, and now we need to find the value of b. So for that, we should make an equation. So x squared is going to be equal to the square root of x. If we square this, we get x power 4 is equal to x, and that is x power 4 minus x equal to 0. X common factor of x power 3 minus 1 equal to 0. And we get the solution x equals 0. And from here, x equals 1. Then we know that b is going to be 1. Now the first volume that we need to calculate is if we were rotating the square root of x around the x-axis. So that would be the first volume, that is pi integral from 0 to 1 of root of x squared with respect to x. And the second volume, the one that we need to subtract from that solid to make it hollow, is the volume of rotating x squared. So that is going to be pi integral from 0 to 1 of x squared dx. Or if we join everything into one integral, we can consider it like pi integral from 0 to 1 of the upper function root x squared minus the bottom function x squared with respect to x. So doing that, we get that the integral is 3 over 10. So the total volume is 3 pi over 10.